Picture this: the Sun suddenly vanishes from space. What happens next? Does Earth immediately fly off into the darkness, or do we continue orbiting an invisible point in space for another 8 minutes until the last rays of sunlight reach us? Your intuition might tell you we'd feel the gravitational change instantly, but for over a century, physicists argued about this exact question. The answer to this seemingly simple question holds the key to understanding the fundamental fabric of reality itself. Today, we're diving deep into one of physics' most fascinating questions. Does gravity really travel faster than the speed of light? If you want to journey deeper into the mysteries of our cosmos, make sure to subscribe to this channel and hit that notification bell. Now let's begin. To understand whether gravity travels faster than light, we first need to understand what gravity actually is. This might seem basic, but trust me, the answer is far stranger than you probably imagine. Most of us grow up learning Newton's version of gravity, where massive objects attract each other through some invisible force that reaches across space. Drop an apple, and Earth's gravity pulls it down. The Moon orbits Earth because gravity tethers it in place. The Sun holds all the planets in their orbits through its immense gravitational pull. Isaac Newton formulated his law of universal gravitation in 1687, and it was remarkably successful. It explained why planets orbit the Sun in ellipses, why the Moon causes tides, and even allowed astronomers to predict the existence of Neptune before they ever saw it, simply by calculating how its gravity affected Uranus's orbit. For over 2 centuries, Newton's gravity reigned supreme as one of science's greatest triumphs. But Newton's gravity had a problem that troubled even Newton himself. In his framework, gravity acted instantaneously across any distance. If the Sun suddenly doubled in mass, Earth would immediately feel the change in gravitational pull. No delay, no travel time, instant action across 93 million miles of empty space. Newton found this deeply unsatisfying. He called it action at a distance, and admitted he couldn't explain how it worked. In his own words, he wrote that the idea of one body acting upon another across empty space is to me so great an absurdity that I believe no man who has, in philosophical matters, a competent faculty of thinking can ever fall into it. Yet despite his discomfort with instantaneous gravity, Newton's equations didn't include any mechanism for gravity to travel at a finite speed. In the Newtonian universe, gravity simply existed everywhere simultaneously, like an invisible scaffolding holding the cosmos together. Change the mass here, and the gravitational field everywhere adjusts instantly. It worked mathematically, predicted observations accurately, but philosophically troubled those who thought deeply about it. For 200 years, this remained an open question. Does gravity propagate at some finite speed, or is it truly instantaneous? Most physicists simply accepted Newton's framework because it worked. Why worry about philosophical problems when the predictions matched reality? But a few minds couldn't let it go. If gravity travels, how fast does it move, and what carries it across the void of space? The first hint that something was wrong with instantaneous gravity came not from studying gravity itself, but from understanding light and electromagnetism. In the 1860s, Scottish physicist James Clerk Maxwell unified electricity and magnetism into a single theory, electromagnetism, and his equations revealed something shocking. They predicted that oscillating electric and magnetic fields would create waves that propagate through space at a specific speed, approximately 186,282 miles per second. Maxwell realized this speed matched the measured speed of light, leading him to propose that light itself is an electromagnetic wave. This was a revolutionary insight, unifying two apparently separate phenomena, light and electromagnetism, into one framework. But for our story, the crucial point is this. Maxwell's equations showed that electromagnetic influences don't act instantaneously. Change an electric charge here, and the electromagnetic field over there doesn't change immediately. Instead, the influence propagates outward at the speed of light. This raised a troubling question. If electromagnetic forces travel at light speed, why should gravity be different? Both are fundamental forces that act across space. Both decrease with distance according to inverse square laws. Yet electromagnetic changes propagate at finite speed, while gravity supposedly acts instantaneously. It seemed inconsistent, as if nature was using two different rule books. Enter Albert Einstein, a 26-year-old patent clerk in Switzerland who would revolutionize our understanding of space, time, and gravity. In 1905, Einstein published his special theory of relativity, which fundamentally reimagined the nature of space and time. The theory rested on two simple postulates. First, the laws of physics are the same for all observers moving at constant velocities. Second, the speed of light is constant for all observers, regardless of how they're moving. From these innocent-sounding principles flowed revolutionary consequences. Space and time aren't separate, absolute entities, but are woven together into a four-dimensional fabric called spacetime. Moving clocks tick slower than stationary ones. Time dilation. Moving objects contract in length, length contraction. And most famously, mass and energy are equivalent, related by the equation E equals mc squared. But for our question about gravity, the most important consequence of special relativity was this: no information, no influence, no causal effect can travel faster than light. The speed of light isn't just the speed at which light happens to travel. It's a fundamental speed limit woven into the structure of space-time itself. Nothing, no matter, no energy, no information, can exceed this cosmic speed limit. This immediately created a problem for Newton's gravity. If gravitational influences acted instantaneously, they would transmit information faster than light, violating special relativity. Imagine the sun suddenly vanishing. In Newton's theory, Earth would immediately fly off on a tangent, instantly responding to the sun's absence. But this would mean Earth knew about an event 93 million miles away with zero time delay, information traveling infinitely fast, violating relativity's speed limit. Einstein recognized this problem and spent the next decade searching for a new theory of gravity compatible with relativity. The result, published in 1915, was the general theory of relativity. One of the most beautiful and profound theories in all of science, general relativity completely reimagined what gravity is. In Einstein's view, gravity isn't a force at all in the traditional sense. Instead, massive objects curve the fabric of space-time itself, and objects moving through this curved space-time follow the straightest possible paths, called geodesics. Earth orbits the Sun not because an invisible force pulls it inward, but because the Sun's mass warps space-time in a way that makes a curved orbit the straightest possible path through that curved geometry. Imagine placing a bowling ball on a stretched rubber sheet. The ball creates a depression, curving the sheet around it. Now roll a marble across the sheet. Instead of traveling in a straight line, the marble curves around the depression, perhaps even orbiting the bowling ball if you give it the right speed. This is a crude analogy for how mass curves space-time and how other objects respond to that curvature. This curvature of space-time by mass isn't just a metaphor, it's real geometry. Clocks run slower in stronger gravitational fields because time itself flows at different rates in curved space-time. Light bends when passing near massive objects because it follows the curves of space-time. And here's the crucial point for our question. Changes in space-time curvature don't propagate instantaneously. They travel outward at a finite speed, and Einstein's equations predicted that speed would be exactly the speed of light. Think about what this means. If the sun suddenly vanished, it wouldn't just disappear from view instantly. The last light rays would continue traveling toward Earth for 8 minutes and 20 seconds, the time light takes to cross 93 million miles. But according to general relativity, Earth wouldn't feel the gravitational change for the same 8 minutes and 20 seconds. The disturbance in space-time curvature would propagate outward at light speed, just like the last light rays. For those 8 minutes, we'd still see the sun and still orbit a point in space where it used to be, completely unaware that anything had changed. This prediction, that gravity propagates at light speed, was built into Einstein's equations from the beginning. It had to be because general relativity was carefully constructed to be compatible with special relativity. The cosmic speed limit applies to everything, including gravity. But proving this prediction observationally would turn out to be extraordinarily difficult, taking over a century and requiring some of the most sensitive instruments ever built. The reason it's so hard to measure the speed of gravity is that gravity is incredibly weak compared to other forces. The electromagnetic force between two electrons is about 1, followed by 42 zeros, times stronger than their gravitational attraction. Gravity only seems strong in everyday life because large objects like Earth contain enormous numbers of particles, and all their tiny gravitational pulls add up. But detecting changes in gravity from cosmic events requires sensitivity that seemed impossible for decades. Einstein himself predicted that accelerating massive objects would create ripples in space-time, gravitational waves that would propagate outward at light speed, carrying energy away from the source. These waves would stretch and squeeze space itself as they passed, but the effect would be minuscule. Einstein calculated that even cataclysmic events like colliding black holes would create distortions in space-time smaller than a fraction of the width of an atomic nucleus. He thought such waves would be impossible to detect and essentially unobservable. For decades, gravitational waves remained theoretical curiosities, mathematical features of Einstein's equations that most physicists thought we'd never actually observe. Some even questioned whether they were real or just artifacts of the mathematical formalism. But a few visionaries believed detection was possible and began working on the seemingly impossible task of building instruments sensitive enough to detect space-time ripples smaller than atoms. The story of gravitational wave detection is one of the great triumphs of human ingenuity and persistence. In the 1960s and 70s, physicist Joseph Weber built the first gravitational wave detectors, massive aluminum cylinders that would ring like bells if a gravitational wave passed through them. Weber claimed to have detected signals, but other physicists couldn't replicate his results. His detections are now considered false alarms, but his pioneering work inspired others to pursue the goal. The real breakthrough came with a different approach: laser interferometry. The idea is elegantly simple but devilishly difficult to implement. You build 2 long tunnels at right angles to each other, forming an L shape. You bounce laser beams back and forth along these tunnels, using mirrors at each end. If a gravitational wave passes through, it will stretch space in one direction while squeezing it in the perpendicular direction. This means one tunnel momentarily becomes longer, while the other becomes shorter. By comparing the laser light in both tunnels, you can detect this tiny change. How tiny? The detectors needed to measure changes in length smaller than 1/10,000th the width of a proton. That's like measuring the distance to the nearest star to an accuracy smaller than the width of a human hair. The technical challenges were staggering. Vibrations from earthquakes, traffic, ocean waves, even quantum fluctuations in the laser light itself could swamp the signal. Building such an instrument required advances in laser technology, optics, vibration isolation, vacuum systems, and data analysis. The LIGO project, the Laser Interferometer Gravitational Wave Observatory, began in the 1992 when the National Science Foundation funded construction of two facilities, one in Louisiana and one in Washington state, separated by nearly 2,000 miles. Each facility has two tunnels, each about 2.5 miles long, forming an L shape. The separation between facilities allows scientists to confirm that detected signals are real gravitational waves rather than local disturbances. LIGO began operations in 2002 but didn't immediately detect anything. The initial sensitivity wasn't quite good enough to catch the faint signals from cosmic events. For years, the detectors ran searching for gravitational waves, finding nothing. Some wondered if the investment, over $1 billion, would ever pay off. But the scientists persisted, gradually upgrading the instruments, improving the sensitivity, and waiting for the universe to reveal its secrets. Then came September 14, 2015. After a major upgrade that increased LIGO's sensitivity tenfold, the detectors had been operating in their advanced configuration for just days when both facilities simultaneously registered a signal. The pattern was unmistakable, a chirp starting at low frequency and rapidly increasing in pitch and amplitude before abruptly cutting off. The signal matched theoretical predictions for two black holes, one 36 times the Sun's mass, the other 29 times, spiraling together and merging into a single black hole 62 times the Sun's mass. Wait, 36 plus 29 equals 65, not 62. Where did those three missing solar masses go? They were converted to pure energy and radiated away as gravitational waves according to Einstein's equation, E equals mc squared. In the final fraction of a second before merger, those colliding black holes radiated more power than all the stars in the observable universe combined. The amount of energy released was staggering, equivalent to converting 3 entire suns into pure gravitational wave energy. This detection, announced publicly in February 2016 after months of careful verification, was a watershed moment in physics. It confirmed that gravitational waves exist, that black holes exist, and merge exactly as Einstein's equations predict, and that we can detect and study cosmic events through an entirely new channel beyond electromagnetic radiation. Rainer Weiss, Barry Barish, and Kip Thorne received the Nobel Prize in Physics in 2017 for this achievement. But for our question about the speed of gravity, the black hole merger didn't provide a definitive answer. Black holes don't emit light, so there was no electromagnetic signal to compare with the gravitational wave arrival time. The observation was consistent with gravity traveling at light speed, but it didn't prove it. To definitively measure the speed of gravity, scientists needed an event that produced both gravitational waves and electromagnetic radiation, and they needed to detect both. That event came on August 17, 2017. LIGO detected a gravitational wave signal different from previous black hole mergers. This signal came from two neutron stars, city-sized balls of matter, each containing more mass than the Sun, spiraling together and colliding. Unlike black holes, neutron stars are made of matter that can emit light. When they collide, they produce spectacular fireworks across the electromagnetic spectrum. Within seconds of LIGO detecting the gravitational waves, the Fermi Gamma Ray Space Telescope detected a burst of gamma rays from the same region of sky. This was the moment scientists had been waiting for: simultaneous detection of gravitational waves and electromagnetic radiation from the same event. Now they could measure how fast gravity travels by comparing the arrival times. Speaking of time and the speed of light, if you're curious about what happens to time itself as you approach this cosmic speed limit, I actually made a whole video exploring, does time stop when you hit the speed of light? It's a mind-bending journey through special relativity that complements what we're discussing here. The link is in the description below, and pinned on the comments. But for now, let's get back to that neutron-star collision and what it revealed about gravity's speed. The neutron stars that merged in August 2017 were located in galaxy NGC 4993, about 130 million light-years from Earth. When I say the collision happened in August 2017, I mean that's when we detected it. The actual collision occurred 130 million years ago. The waves have been traveling through space all that time, carrying information about an event that happened when dinosaurs were just beginning to diversify on Earth. The gravitational waves from the merger traveled for 130 million years before reaching our detectors. The electromagnetic radiation, gamma rays, X-rays, visible light, infrared, radio waves traveled the same distance. If gravity traveled faster or slower than light, there should be a time difference between when the gravitational waves arrived and when the electromagnetic signals arrived. Even a tiny difference in speed would accumulate over 130 million light-years into a detectable time gap. So what did scientists find? The gravitational waves arrived about 1.7 seconds before the gamma ray burst. At first glance, this might seem like gravity traveled faster than light. But that tiny time difference has nothing to do with different propagation speeds through space. Instead, it reflects what happened at the source. The gravitational waves were generated during the final moments of the merger when the neutron stars were spiraling together. The gamma rays were produced slightly later after the stars had already collided from processes in the resulting explosion. Think of it like thunder and lightning. You see the lightning flash, then hear the thunder a few seconds later. This doesn't mean light travels faster than sound through space. It means the light is produced the instant the lightning strikes, while the sound is generated by the expanding shock wave that takes a moment to form. Similarly, gravitational waves are produced during the merger itself, while gamma rays are produced in the aftermath. The 1.7-second delay tells us about the physics of neutron-star collisions, not about different speeds of propagation. When scientists carefully analyzed the arrival times, accounting for the different generation mechanisms, they found something remarkable. Gravitational waves and light arrived within an extraordinarily tight window. The analysis showed that the speed of gravity must be within about 3 parts in 100,000 trillion of the speed of light. Let me put that another way. Gravity travels at 99.999% the speed of light, or possibly even faster by an equally tiny amount. In other words, for all practical purposes, gravity travels at exactly the speed of light. This measurement represents one of the most precise confirmations of general relativity ever achieved. Einstein predicted in 1915 that gravity propagates at light speed, and 102 years later, humanity finally proved him right by detecting ripples in space-time from a cataclysm 130 million light-years away. It's a testament to both Einstein's theoretical genius and the extraordinary capabilities of modern science. But this raises a deeper question. Why does gravity travel at exactly the speed of light? Is this just a coincidence, or is there something fundamental connecting these phenomena? The answer reveals profound truths about the structure of reality itself. The speed of light isn't really about light, it's about causality, the flow of information, and the structure of space-time. In relativity, the speed of light is more accurately called the speed of causality, the maximum speed at which cause can influence effect. It's the speed at which massless particles travel, the speed at which information propagates, the speed that connects space and time into space-time. Light travels at this speed because photons are massless. Gravitational waves travel at this speed because they too carry no mass. The speed itself is a fundamental feature of how the universe is put together. Here's where it gets really interesting. In quantum field theory, the framework combining quantum mechanics with special relativity, every force is mediated by particles. Electromagnetism is carried by photons. The strong nuclear force is carried by gluons. The weak nuclear force is carried by W and Z bosons. And gravity? It should be carried by gravitons, hypothetical, massless particles that transmit gravitational interactions. We've never detected an individual graviton, and doing so would require technology far beyond our current capabilities. Gravitons interact so weakly with matter that they pass through virtually everything unaffected. But if gravitons exist and are massless, as theory suggests, they would travel at exactly the speed of light. A gravitational wave would be a coherent stream of countless gravitons all moving at light speed. The observation that gravitational waves travel at light speed is strong evidence that gravitons, if they exist, are indeed massless. This connects to one of the deepest mysteries in physics. Why do some particles have mass while others don't? The Higgs boson, discovered at the Large Hadron Collider in 2012, provides mass to particles like electrons and quarks through their interaction with the Higgs field. But photons and gravitons don't interact with the Higgs field, so they remain massless and travel at the cosmic speed limit. The fact that gravity travels at light speed tells us something fundamental about how gravity fits into the quantum picture of the universe. Now let's address something that might be bothering you. I've been saying gravity propagates at light speed, which means changes in gravitational fields spread outward at finite speed. But doesn't this create the same problem that troubled Newton? Planets not orbiting where the Sun actually is, but where it was 8 minutes ago. How can the solar system remain stable if each planet responds to the Sun's outdated position? This is an excellent question, and the answer involves a subtle but crucial aspect of general relativity. While it's true that gravitational changes propagate at light speed, the steady-state gravitational field of a uniformly moving object extends outward from where the object is now, not where it was. This seems paradoxical, but it emerges naturally from the mathematics of general relativity. Think of it this way: Earth orbits the Sun in a nearly circular path. The Sun is also moving through space, orbiting the galactic center. But the Sun's motion is essentially uniform. It's not accelerating significantly. For a uniformly moving source, general relativity predicts that the gravitational field points toward the current position of the source, not its retarded position. Only changes in the gravitational field, caused by accelerations, propagate outward at light speed. This is analogous to electromagnetism. An electron moving at constant velocity produces an electric field that points to where the electron is now. Only if the electron accelerates does it generate electromagnetic waves that carry information about the acceleration outward at light speed. Similarly, a mass moving at constant velocity produces a gravitational field pointing to its current location. Accelerating masses generate gravitational waves that propagate at light speed. The Sun's slow orbital motion around the galaxy counts as nearly uniform motion. It accelerates slightly due to the galactic gravitational field, but this acceleration is so gentle that its effects are negligible. Earth orbits the position where the Sun is now, not where it was 8 minutes ago, even though gravitational influences travel at light speed. This delicate mathematical balance is one of general relativity's beautiful features. The theory ensures that slowly moving objects orbit accurately without requiring instantaneous gravity. But what if the Sun did suddenly accelerate or change mass? Then the change would propagate outward at light speed. For 8 minutes and 20 seconds, Earth would continue orbiting the old gravitational field configuration. Only when the gravitational waves reached us would we feel the change and adjust our orbit accordingly. During those 8 minutes, we'd still see the Sun as it was and feel the gravitational field as it was. Cause and effect would be properly ordered, no information traveling faster than light. This highlights something profound. The universe is constructed in a deeply consistent way. Special relativity sets a cosmic speed limit. General relativity describes gravity as curved spacetime, and this automatically ensures gravitational influences respect the speed limit. Quantum field theory suggests forces are mediated by particles, and massless force carriers travel at light speed. All these frameworks fit together seamlessly, each supporting and reinforcing the others. Nature appears to be governed by a coherent set of principles, not arbitrary rules. The observation of gravitational waves traveling at light speed also opens up entirely new ways of studying the universe. Before 2015, astronomy was done almost exclusively with electromagnetic radiation, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. These are all forms of light, just at different energies. Astronomers were like people watching a symphony but only able to hear the violins. Gravitational wave astronomy lets us hear the bass notes, the deep rhythms of massive objects moving through space-time. Electromagnetic waves are easily absorbed and scattered. Light from distant galaxies can be blocked by dust clouds, but gravitational waves pass through matter almost unaffected. They carry information from the most violent events in the cosmos directly to our detectors, unimpeded by anything in between. We can observe phenomena that are electromagnetically invisible, like black hole mergers, or see events from perspectives impossible with light alone. The neutron star merger observed in August 2017 demonstrated the power of multi-messenger astronomy, observing the same event through both gravitational waves and electromagnetic radiation. The gravitational waves told us about the masses of the stars, their orbital evolution, and the merger dynamics. The electromagnetic observations revealed the composition of ejected material, the creation of heavy elements, and the expansion of the debris. Together, these observations provided insights neither could achieve alone. In the aftermath of the neutron star collision, telescopes around the world and in space observed the fireworks. About 10 hours after the merger, optical telescopes in Chile captured the first light from what's called a kilonova, an explosion powered by radioactive decay of freshly synthesized heavy elements. The glow changed color over subsequent days, from blue to red, as different elements decayed at different rates. Spectroscopic analysis confirmed the presence of gold, platinum, and other heavy elements being forged in the explosion. This observation solved a long-standing mystery: where do the heaviest elements in the universe come from? Elements lighter than iron are created in stellar cores through fusion. Iron itself is created in the final stages of massive star evolution. But creating elements heavier than iron requires intense neutron bombardment in what's called rapid neutron capture, or the R process. Scientists suspected neutron star mergers as a site for R process nuclear synthesis, but the 2017 observation provided the first direct confirmation. The gold in wedding rings, the platinum in jewelry, and catalytic converters, the rare earth elements in smartphones, all were forged in neutron star collisions billions of years ago, scattered through space, incorporated into the gas clouds that eventually formed our solar system, concentrated in Earth during its formation, and finally extracted and shaped by human hands. You're connected to these cosmic cataclysms in the most direct way imaginable. The atoms in your body remember the violence of their creation. Since that groundbreaking detection in 2017, LIGO and its partner detector, Virgo in Italy, have observed dozens of gravitational wave events. Most are black hole mergers, but a few are neutron star mergers, or possibly black holes colliding with neutron stars. Each detection refines our understanding of these extreme cosmic phenomena and tests general relativity under conditions impossible to replicate on Earth. Every observation confirms that gravitational waves travel at light speed, exactly as Einstein predicted. The consistency is remarkable. Whether the waves come from black holes 30 times the Sun's mass or neutron stars just over one solar mass, whether the source is 1 billion light-years away or 130 million, whether the merger takes seconds or minutes, in every case, the waves propagate at the speed of light to within measurement precision. This consistency across different sources and distances tells us something important. The speed of gravity isn't some arbitrary property that might vary depending on circumstances. It's a fundamental feature of how the universe works, as invariant and universal as the speed of light itself. In fact, they're the same speed because they're both manifestations of the same underlying principle, the cosmic speed limit built into the structure of space-time. But here's something that might make your brain hurt in the best possible way. While gravity travels at light speed, gravitational effects can appear to propagate faster than light in certain situations due to the curvature of space-time itself. This sounds like a contradiction, but it's not. It's a consequence of general relativity's geometric nature. Imagine a wormhole, a hypothetical tunnel through space-time connecting two distant points. If such a structure existed, you could potentially travel from one point to another faster than light could travel through normal space between those points. But you wouldn't be moving faster than light locally. You'd still be limited to light speed, or slower. You'd simply be taking a shortcut through curved space-time, like drilling through a mountain instead of driving over it. Similarly, in the early universe during cosmic inflation, space itself expanded faster than light. This doesn't violate relativity because space itself can stretch as fast as it wants. The speed limit applies to objects moving through space, not to the expansion of space itself. Galaxies far enough away are receding from us faster than light due to cosmic expansion, yet they're not moving through their local space faster than light. These subtleties remind us that general relativity is fundamentally different from our everyday intuition about space and time. Space-time is a dynamic, flexible thing that can curve, stretch, and warp. The rules governing motion through space-time are different from the rules governing space-time itself. Gravity doesn't travel through space at light speed. Gravity is the curvature of space-time, and changes in that curvature propagate at light speed. Let me share something that perfectly captures how revolutionary gravitational wave astronomy has become. Before LIGO's first detection in 2015, we had never directly observed a black hole merger. We had strong theoretical reasons to believe such mergers occurred, but no direct evidence. In the 6 years since that first detection, we've observed over 90 confirmed gravitational wave events, most of them black hole mergers. We've gone from 0 direct observations to statistical studies of merger populations. These observations have revealed surprises. Black holes come in a wider range of masses than expected. Some mergers involve black holes with surprisingly different masses, one much heavier than the other. One event, designated GW1 90521, might have been a black hole merging with a neutron star, or possibly two neutron stars. The mass was right at the boundary, making classification uncertain. Each observation raises new questions even as it answers old ones. The observation that gravity travels at light speed also constrains theories that attempt to modify or extend general relativity. Many physicists suspect general relativity isn't the final word on gravity. At quantum scales, in the centers of black holes, or during the Big Bang, general relativity breaks down and must be replaced or supplemented by a quantum theory of gravity. Various candidates exist: string theory, loop quantum gravity, and others. Many of these theories predict small modifications to general relativity's predictions. Perhaps gravitational waves travel at slightly different speeds depending on their frequency. Perhaps the speed of gravity varies slightly with the strength of the gravitational field. Perhaps there are extra polarizations of gravitational waves beyond the two predicted by general relativity. The observations rule out many of these modifications, showing that if general relativity is wrong, it's wrong in very subtle ways we haven't yet detected. The precision with which we've measured the speed of gravity, matching light speed to within 3 parts in 100,000 trillion, is extraordinary. To appreciate this precision, imagine measuring the distance from Earth to the Sun to within the width of a human hair. That's the level of accuracy achieved. This precision comes from combining 3 factors: the enormous distance the waves traveled, giving tiny speed differences time to accumulate into measurable delays, the precise timing of both gravitational wave and electromagnetic detectors, and careful theoretical modeling of when each type of signal should be produced. Some proposed theories of modified gravity predicted gravitational waves should travel slower than light. The neutron star merger observation ruled out these theories in a single stroke. This is how science progresses, not just through confirming predictions, but through ruling out alternatives. Each observation narrows the space of viable theories, guiding us toward a more accurate understanding of reality. The fact that gravity travels at light speed also has implications for dark energy, the mysterious force accelerating cosmic expansion. Some theories propose that gravity's behavior changes over cosmic distances or in weak gravitational fields, and these modifications might explain cosmic acceleration without invoking dark energy. But if gravity propagates at exactly light speed, as observed, these theories face severe constraints. The observations are forcing theorists to reconsider or abandon models that predicted different propagation speeds. Let's talk about what would happen if gravity didn't travel at light speed. If gravity propagated faster than light, it would violate causality, the principle that cause precedes effect. You could potentially send signals backward in time by combining gravitational signals traveling faster than light with electromagnetic signals traveling at light speed, creating logical paradoxes. The universe would become inconsistent, allowing impossible situations. If gravity traveled slower than light, the solar system would be unstable. Planets would respond to the Sun's outdated position, causing their orbits to gradually spiral outward or inward. The Earth-Moon system would be unstable. Binary stars would lose orbital energy differently than observed. The universe we see, with stable planetary systems lasting billions of years, wouldn't exist. The fact that our solar system is 4.6 billion years old and still stable is indirect evidence that gravity propagates at the right speed to maintain stability. Some people have wondered whether quantum entanglement, where measuring one particle instantly affects its entangled partner, regardless of distance, might allow faster-than-light communication, or might show that some influences propagate faster than light. This is a deep misconception. Quantum entanglement doesn't transmit information faster than light. You can't use entanglement to send messages or signals. The correlations between entangled particles are real and instantaneous, but they can't be used to violate causality or transmit information faster than light. Similarly, the quantum phenomenon of tunneling, where particles can pass through barriers they classically shouldn't be able to cross, sometimes appears to happen faster than light. But careful analysis shows that while a particle's average position might shift faster than light during tunneling, no information or causal influence propagates faster than light. These quantum effects are subtle and don't violate relativity when properly understood. The cosmic speed limit is robust and appears to be truly universal. In over a century since Einstein proposed special relativity, countless experiments have looked for violations. Particles have been accelerated to 99.99999% of light speed at the Large Hadron Collider. Astronomical observations have studied light from gamma-ray bursts billions of light-years away. Neutrinos have been studied in detail, a famous experimental error in 2011 briefly suggested neutrinos traveled faster than light, but careful reanalysis found a faulty cable connection and confirmed neutrinos respect the speed limit. Every test confirms the same conclusion: nothing travels faster than light. Not electromagnetic waves, not gravitational waves, not particles, not information, not causality itself. The speed of light is woven into the fundamental structure of spacetime. It's not just a speed, it's the conversion factor between space and time, the rate at which time transforms into space in space-time geometry. Here's something beautiful to contemplate. When we observe gravitational waves from a neutron star merger 130 million light-years away, we're detecting a change in space-time curvature that's been propagating toward us for 130 million years. The ripples passed through millions of galaxies, clusters, and voids. They stretched and squeezed space along their entire journey. And when they finally reached Earth, they changed the distance between LIGO's mirrors by less than 1,000th the width of a proton. That we can detect something so unimaginably tiny is a testament to human ingenuity. That the universe produces signals we can detect despite their faintness is a stroke of cosmic fortune. That the detections confirm century-old theoretical predictions is a validation of mathematics and reason as tools for understanding reality. And that these observations connect us to violent events in the distant cosmos, showing us the universe's grandest dramas, fills me with awe. The gravitational waves carrying information about colliding neutron stars are the same waves Einstein predicted in 1916 when World War I raged and most scientists still questioned whether atoms existed. He developed general relativity using nothing but thought, mathematics, and the principle that the laws of physics should be the same for all observers. From these abstract considerations, he derived concrete predictions about how massive objects curve space-time and create propagating ripples. A century later, we confirmed he was right. This speaks to something profound about the nature of scientific discovery. Einstein never saw a black hole, never observed a neutron star, never witnessed a gravitational wave detector. He died in 1955, 60 years before LIGO's first detection. Yet through pure reasoning about the fundamental principles governing space and time, he predicted phenomena that wouldn't be observed until generations after his death. This is the power of theoretical physics at its finest, using mathematics as a telescope to see truths about reality that observations can't yet reveal. But general relativity isn't perfect. We know this because it's fundamentally incompatible with quantum mechanics, the other great pillar of modern physics. Quantum mechanics governs the microscopic world of atoms and particles with extraordinary precision. General relativity governs gravity and cosmic scales with equal precision. Yet these two theories use completely different mathematical frameworks and make contradictory assumptions about the nature of reality. Quantum mechanics says certain properties are fundamentally uncertain and probabilistic. General relativity treats spacetime as a smooth, deterministic geometry. Quantum mechanics works in flat spacetime. General relativity is all about curved spacetime. When you try to combine them, when you need both quantum mechanics and gravity, like inside black holes or during the Big Bang, the mathematics breaks down, giving nonsensical, infinite results. Physicists have been searching for a theory of quantum gravity for decades. String theory proposes that fundamental particles are actually tiny vibrating strings, and gravity emerges from a particular vibration mode. Loop quantum gravity suggests spacetime itself is quantized at the smallest scales, made of discrete chunks rather than being continuous. Other approaches exist, each with strengths and weaknesses, none yet definitively confirmed by observation. Gravitational wave observations might help distinguish between these theories. Different quantum gravity theories make different predictions about how gravity behaves, at high energies or in strong fields. They might predict subtle dispersion, higher frequency gravitational waves traveling at slightly different speeds than lower frequencies. They might predict extrapolarizations of gravitational waves or tiny violations of general relativity's predictions. As detectors become more sensitive and observe more extreme events, these subtle effects might become detectable. The next generation of gravitational wave detectors is already being planned. The Einstein telescope, proposed for construction in Europe, would be 10 times more sensitive than current detectors and able to observe neutron star mergers from across the observable universe. The Cosmic Explorer, proposed for the United States, would have 40-kilometer arms, 16 times longer than LIGO's, providing exquisite sensitivity. These future instruments would detect thousands of gravitational wave events per year rather than dozens. Space-based gravitational wave detectors offer even more exciting possibilities. LISA, the Laser Interferometer, space antenna scheduled for launch in the 2030s, will consist of 3 spacecraft separated by millions of kilometers, forming a giant triangular detector in space. LISA will be sensitive to lower frequency gravitational waves than ground-based detectors can observe, opening entirely new windows on the universe. LISA will detect supermassive black hole mergers, million and billion solar mass behemoths colliding when galaxies merge. It will observe compact binary stars throughout our galaxy. It might even detect gravitational waves from cosmic strings or phase transitions in the early universe, if such exotic phenomena exist. And with every observation, it will measure the speed of gravity, testing whether Einstein's prediction holds across all frequencies and sources. These future observations will probe gravity in regimes we've never accessed. The black hole mergers observed so far involve objects tens of times the Sun's mass. Supermassive black hole mergers involve objects millions of times more massive, creating far stronger gravitational fields. If general relativity breaks down or needs modification at extreme scales, these observations might reveal it. Every new observation is a test of our understanding, an opportunity to find cracks in our theories. Let me tell you about something that beautifully illustrates how gravitational wave observations test fundamental physics. When LIGO detected the first black hole merger, they didn't just measure the masses and spins. They tested whether the signal matched general relativity's predictions through the entire merger and ring down, the period after merger when the resulting black hole settles into its final state like a struck bell ringing. General relativity makes precise predictions about ring-down frequencies. A black hole with a particular mass and spin should ring at specific frequencies determined entirely by those two properties. It's like how a bell's tone depends on its size and shape. LIGO measured the ring-down frequencies and confirmed they matched general relativity's predictions to high precision. This tested general relativity in the strong field, highly dynamic regime, exactly where you might expect it to fail if it needs modification. Every aspect of gravitational wave signals provides tests of general relativity. The in-spiral phase, when the objects spiral closer, tests how gravity affects orbital dynamics. The merger phase tests gravity in the most extreme conditions, when spacetime curvature is strongest and changing most rapidly. The ring-down tests how spacetime responds after violent disturbances. Across all phases, general relativity passes every test. Einstein's theory, now over a century old, remains undefeated. But here's what keeps physicists humble. We've only tested general relativity in a limited range of conditions. Most tests involve relatively weak gravitational fields, the solar system, binary pulsars, gravitational wave sources that are extreme by everyday standards, but mild compared to what might exist in nature. We've never observed gravity inside a black hole event horizon, where general relativity predicts infinities. We don't know how gravity behaved during the Big Bang's first moments. In these regimes, general relativity might fail, requiring new physics. The question of whether gravity travels at light speed connects to these deeper mysteries. The speed of gravity is determined by the structure of space-time itself, by how space and time are woven together into a unified fabric. If space-time structure is different than general relativity assumes, perhaps discrete at small scales or higher dimensional, or woven from more fundamental entities, the speed of gravity might differ from light speed under conditions we haven't yet probed. Current observations constrain the speed of gravity to match light speed to extraordinary precision in the conditions we've observed. But what about in the intense gravitational field just outside a black hole event horizon? What about in the first trillionth of a second after the Big Bang? What about in hypothetical regions where space-time tears or folds? These are the frontiers where our understanding remains uncertain, where future observations might surprise us. Let's explore what happens to gravitational waves as they travel through space for millions or billions of years. Unlike electromagnetic waves, which can be absorbed, scattered, or redshifted by matter and energy they encounter, gravitational waves pass through almost everything unaffected. They interact so weakly with normal matter that the entire Earth is essentially transparent to them. This is both a blessing and a curse for astronomers. It's a blessing because gravitational waves carry pristine information from their sources. The waves detected from neutron star mergers traveled 130 million light-years through galaxies, dust clouds, and gas without being significantly affected. What we detect is essentially what was emitted, allowing us to study the source in exquisite detail. It's a curse because it makes gravitational waves extremely hard to detect. If they pass through matter easily, it's hard to build a detector that responds to them. However, gravitational waves are affected by cosmic expansion. As they travel through expanding space, their wavelengths stretch along with space itself, just like electromagnetic waves. This gravitational wave redshift provides information about the cosmic expansion history. By observing gravitational waves from sources at different distances, and therefore different epochs in cosmic history, astronomers can trace how fast the universe has been expanding over time. This offers a completely independent way to measure the expansion rate and test cosmological models. Current controversies about the exact expansion rate, the Hubble constant, might be resolved by gravitational wave observations from numerous sources at various distances. The waves carry a standard siren signal. Their amplitude and frequency encode information about the source's distance, allowing distance measurements without relying on the traditional cosmic distance ladder. The neutron star merger observed in 2017 provided one of the first gravitational wave measurements of the Hubble constant. By measuring the gravitational wave amplitude to determine distance and observing the electromagnetic counterpart to measure redshift, astronomers calculated the expansion rate. The result fell between two conflicting measurements from other methods, suggesting gravitational wave observations might help resolve current tensions in cosmology. Future observations with more sensitive detectors observing hundreds or thousands of events will dramatically improve these measurements. We'll be able to trace cosmic expansion history from the present back billions of years, testing whether dark energy's properties have changed over time or whether our cosmological model needs revision. Gravitational waves will become not just a tool for studying compact objects, but a probe of the universe's large-scale structure and evolution. Here's something that might blow your mind. Gravitational waves can, in principle, carry information from before the cosmic microwave background radiation was released. The CMB, the oldest light we can observe, comes from roughly 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and light to travel freely. Before that, the universe was opaque to electromagnetic radiation, like trying to see through dense fog. But gravitational waves can pass through this fog. If gravitational waves were produced in the early universe by cosmic inflation, phase transitions, or primordial black holes, they would have propagated freely from the start. Detecting primordial gravitational waves would give us a direct view of the universe's first moments, opening a window that electromagnetic astronomy can never access. It would be like gaining a new sense, perceiving aspects of reality previously hidden from us. LIGO and Virgo are not currently sensitive enough to detect primordial gravitational waves. Those would be much fainter than signals from merging black holes. But future detectors, especially space-based ones like LISA, might have the sensitivity needed. Finding primordial gravitational waves would be as revolutionary as the discovery of the cosmic microwave background radiation was in 1964. It would confirm theories about the universe's earliest moments and potentially reveal the physics governing reality at energies far beyond what particle accelerators can reach. The search for primordial gravitational waves also connects to cosmic inflation, the theory that the universe underwent exponential expansion in the first fraction of a second after the Big Bang. Inflation would have produced gravitational waves with a characteristic spectrum, a unique fingerprint that would distinguish them from other sources. Detecting this signature would confirm inflation and provide clues about the energy scale and physics driving it. Some researchers are also searching for gravitational waves in the cosmic microwave background itself. Gravitational waves from inflation would have left imprints on the CMB, subtle patterns in its polarization that several experiments are trying to detect. In 2014, a team announced they had found these imprints, but the signal turned out to be contamination from dust in our galaxy. The search continues with improved instruments and better methods for distinguishing true signals from foreground contamination. Let me share something about how gravitational wave observations are changing our understanding of black hole populations. Before LIGO, we knew about stellar mass black holes from X-ray binary systems, stars orbiting invisible companions whose masses indicated black holes. These observations suggested stellar mass black holes range from about 5 to 20 solar masses. But LIGO has detected black holes ranging from about 5 solar masses up to over 100 solar masses, with many in the previously empty range between 20 and 50 solar masses. This revealed that our previous census of black holes was incomplete. We were only seeing black holes in binary systems with normal stars, where gas flowing onto the black hole produces X-rays we can detect. Isolated black holes, or black holes in binary systems with other black holes, remained invisible to electromagnetic astronomy. Gravitational waves revealed this hidden population, showing us the universe contains far more massive black holes than we realized. Some of the black holes LIGO detected are so massive they challenge stellar evolution theory. Stars in the mass range that should produce 40 to 60 solar mass black holes are thought to undergo pair instability supernovae, completely destroying themselves and leaving no remnant. Yet LIGO has detected black holes in exactly this mass range. Either our understanding of stellar evolution needs revision, or these black holes formed through some other process, perhaps hierarchical mergers, where smaller black holes merge to form larger ones. This is how science progresses. Observations challenge theories. Theories are revised or replaced to account for new observations. The cycle continues, each iteration bringing us closer to accurate understanding. The beauty is that we're never done. There's always more to discover, always deeper questions to ask, always new mysteries arising from solved ones. The observation that gravity travels at light speed also has implications for how we think about the universe's earliest moments. In the standard Big Bang model, the universe began in an extremely hot, dense state and has been expanding and cooling ever since. In the first fraction of a second, temperatures and energies were so high that our current physics theories can't reliably describe what was happening. We need quantum gravity to understand those moments. Different quantum gravity theories make different predictions about that earliest epoch. Some suggest space and time themselves emerged from something more fundamental. Others propose the universe bounced from a previous contracting phase rather than beginning from a singularity. Still others suggest our universe is part of a larger multiverse. Each theory makes predictions about observable consequences, patterns in the cosmic microwave background, distributions of matter, and potentially gravitational wave signatures. By precisely measuring how gravity behaves today, including confirming it travels at light speed, we constrain what could have happened in the early universe. If gravity propagated faster or slower than light during cosmic inflation, it might have left traces in primordial gravitational waves or other observables. The fact that gravity travels at exactly light speed today suggests it did so in the past as well, ruling out certain exotic theories about the early universe. Here's something that connects the speed of gravity to practical technology in a surprising way: GPS satellites. The global positioning system relies on extremely precise timing. Satellites carry atomic clocks and broadcast time signals. Your GPS receiver compares signals from multiple satellites to determine your position. For this to work accurately, the satellite clocks must be synchronized to better than 100 nanoseconds. But general relativity affects those clocks in two ways. First, time dilation from the satellite's orbital motion makes their clocks run slower than ground clocks by about 7 microseconds per day. Second, gravitational time dilation. The satellites are higher in Earth's gravitational field, where time flows faster, makes their clocks run faster by about 45 microseconds per day. The net effect is that satellite clocks run about 38 microseconds per day faster than ground clocks. If GPS didn't account for general relativity, position errors would accumulate at about 10 kilometers per day. Within hours, GPS would be useless. The fact that GPS works so well is a daily confirmation that general relativity correctly describes gravity, space-time curvature, and time dilation. Every time you use navigation on your phone, you're relying on Einstein's theory being correct. It's a beautiful example of how understanding fundamental physics enables practical technology. The speed of gravity also affects how we think about extreme cosmic phenomena. Consider a supernova, a star exploding with the brightness of 1 billion suns. The explosion is triggered when the star's core collapses, usually forming a neutron star or black hole. The gravitational waves from core collapse travel outward at light speed. The neutrinos produced in the collapse escape almost immediately, also traveling at nearly light speed. The shock wave takes hours to reach the star's surface, at which point the supernova becomes visible. If we could detect gravitational waves from supernova, something just beyond current capabilities, we could observe the core collapse itself in real time, hours before the explosion becomes visible. We'd gain a direct view of neutron star or black hole formation, testing our understanding of nuclear physics under extreme conditions. The fact that gravitational waves, neutrinos, and light all travel at the same speed — neutrinos have tiny masses and travel at 99.999% of light speed — means different messengers arrive nearly simultaneously, but carry different information about the event. This multi-messenger approach, combining gravitational waves, electromagnetic observations, and neutrino detections, is revolutionizing astronomy. The neutron-star merger in 2017 demonstrated the power of this approach. Future detections will be even better coordinated. When LIGO detects a neutron-star merger, alerts go out within seconds to telescopes worldwide. Robotic telescopes slew to the position automatically, capturing the earliest light. This coordination has transformed how astronomy is done, from individual observers to global networks responding to alerts in real time. Let me tell you about something that captures the human drama behind these discoveries. When LIGO made its first detection in September 2015, the signal was so clear that some scientists initially thought it might be a fake, a blind injection where fake signals are sometimes added to the data stream to test whether the analysis pipeline works correctly. Only after verifying that no blind injection had been made did the team believe the signal was real. The months between detection and public announcement in February 2016 were filled with careful analysis, checking and rechecking every aspect of the observation. Scientists verified that both detectors saw the same signal. They ruled out environmental causes, earthquakes, lightning, airplane flyovers, anything that might create a false signal. They analyzed the waveform, confirming it matched theoretical predictions. They calculated the probability of the signal being random noise, less than 1 in 3.5 million. Only when they were absolutely certain did they announce the discovery. This caution reflects how science really works. Popular portrayals often show scientists making dramatic discoveries and immediately announcing them to the world. Reality is more careful. Extraordinary claims require extraordinary evidence. Before announcing a discovery that will be remembered for centuries, you must be certain. The LIGO team's meticulous verification before announcement exemplifies scientific rigor at its best. The discovery's announcement created worldwide excitement. Press conferences, news coverage, social media reactions. People around the globe celebrated this confirmation of Einstein's century-old prediction. It was a rare moment when abstract physics broke through to public consciousness, capturing imaginations and inspiring wonder. The scientists involved became celebrities overnight, appearing on talk shows and magazine covers, explaining gravitational waves to audiences who had never heard the term before. But beyond the public celebration, the scientific impact was profound. Papers analyzing the detection, its implications, and what it revealed about black holes and general relativity appeared by the hundreds. The observations spawned new research directions, prompted re-evaluation of theoretical models, and motivated improvements to detectors. A single observation catalyzed progress across multiple fields: astrophysics, cosmology, gravitational physics, and even quantum optics. The Nobel Prize in Physics 2017 went to Rainer Weiss, Barry Barish, and Kip Thorne for decisive contributions to the LIGO detector and the observation of gravitational waves. The award recognized not just the detection itself, but the decades of work developing the technology and building the instruments. It acknowledged that great discoveries often require sustained effort over entire careers, collaboration among thousands of scientists, and perseverance through setbacks and skepticism. Weiss conceived the basic idea of laser interferometric gravitational wave detection in the early 1970s. Thorne championed the theoretical understanding of gravitational wave sources and worked to convince the scientific community that detection was possible. Barish led LIGO through crucial years of construction and upgrade, managing the complex project and building the collaboration. Their collective efforts, and those of thousands of colleagues, made the discovery possible. This reminds us that science is fundamentally a human endeavor. Yes, it's about understanding nature, testing theories, and seeking truth. But it's also about people, their curiosity, creativity, persistence, and collaboration. The confirmation that gravity travels at light speed isn't just a fact about the universe, it's a testament to human ingenuity, our ability to ask deep questions and find answers, our capacity to build instruments of extraordinary precision, and our drive to understand the cosmos we inhabit. The confirmation that gravity propagates at light speed also reshapes how we think about the relationship between gravity and the other fundamental forces. Physics recognizes 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. 3 of these, electromagnetism, strong and weak, have been unified in the standard model of particle physics, a quantum field theory describing how particles and forces interact. Gravity stands apart. Despite over a century of effort, physicists haven't successfully incorporated gravity into a quantum framework compatible with the standard model. This isn't just an academic problem, it suggests our understanding of fundamental physics is incomplete. The fact that gravitational waves travel at exactly light speed, just like electromagnetic waves, hints that gravity might be more similar to other forces than its stubborn resistance to quantization suggests. In quantum field theory, forces arise from particles exchanging virtual particles. Electromagnetism comes from exchanging photons. The strong force comes from exchanging gluons. The weak force comes from exchanging W and Z bosons. If gravity follows the same pattern, it should involve exchanging gravitons, hypothetical particles carrying the gravitational force. For the mathematics to work consistently, gravitons must be massless, which automatically means they travel at light speed. We've never detected individual gravitons and likely never will with any conceivable technology. Gravitons interact so weakly that they pass through entire planets, as if nothing were there. A detector capable of reliably catching single gravitons would need to be so massive it would collapse into a black hole under its own gravity. Yet the graviton concept remains useful theoretically, and the observation that gravitational waves travel at light speed supports the idea that gravitons, if they exist, are indeed massless. String theory, one approach to quantum gravity, automatically predicts massless gravitons as vibration modes of fundamental strings. Loop quantum gravity predicts discrete quanta of spacetime geometry that collectively produce gravitational effects. While these theories differ in their fundamental assumptions and mathematical structures, both predict that macroscopic gravity should propagate at light speed. The observations confirm this prediction without distinguishing which theory, if either, correctly describes quantum gravity. The speed of gravity also connects to one of physics' deepest puzzles. Why is gravity so incredibly weak compared to other forces? An electron and a proton attract each other electromagnetically with a force about 1 followed by 42 zeros times stronger than their gravitational attraction. Why such an enormous disparity? Various theories attempt to explain this hierarchy problem, and some suggest answers involving extra dimensions or different fundamental structures of reality. One intriguing proposal suggests gravity is weak because it leaks into extra spatial dimensions we can't directly perceive. In these theories, electromagnetism and the other forces are confined to our familiar 3 spatial dimensions, but gravity spreads through additional hidden dimensions, diluting its strength in our 3-dimensional space. If true, gravity might behave differently at very short distances or very high energies where effects of extra dimensions become noticeable. These theories make testable predictions. If extra dimensions exist, gravitational waves at very high frequencies might propagate differently than low-frequency waves as they probe shorter distances where extra dimensions could affect propagation. Future observations with more sensitive detectors might detect these subtle differences, or their absence might rule out certain extra-dimensional theories. Each observation refines our understanding and narrows the space of viable theories. Let me share something about the computational challenges in gravitational wave astronomy. Detecting and analyzing gravitational wave signals requires comparing observed data to theoretical templates, predicted waveforms for various types of sources. But generating these templates demands solving Einstein's equations for 2 massive objects orbiting and merging, which is extraordinarily difficult. Einstein's equations are 10 coupled nonlinear partial differential equations relating spacetime curvature to matter and energy. For simple cases like non-rotating black holes or weak gravitational fields, approximate solutions exist. But for 2 massive black holes spiraling together, no analytical solution exists. The equations must be solved numerically using supercomputers, simulating how spacetime evolves as the black holes orbit and merge. These numerical relativity simulations only became possible in the 2000s, after decades of development. The breakthrough came in 2005 when multiple research groups finally achieved stable simulations of merging black holes. This was just 10 years before LIGO's first detection, remarkably good timing. Without the templates from numerical relativity, identifying gravitational wave signals in noisy data would have been nearly impossible. The computational effort is staggering. Simulating a single black hole merger can require weeks of supercomputer time. To create a template bank covering all possible masses, spins, and orbital configurations requires hundreds of thousands of simulations. This represents one of the largest computational efforts in physics, rivaling particle physics simulations in scope and complexity. Yet it's essential for extracting science from observations. When LIGO detects a candidate signal, automated pipelines compare it to template banks, searching for the best match. Within minutes, the system identifies the most likely source parameters: masses, spins, distance, position in the sky. This rapid analysis enables quick alerts to electromagnetic telescopes, allowing them to search for possible counterparts while transient emission is still bright. The entire process, from detection to alert to telescope response, happens faster than you could drive across a city. This automation and coordination represent a triumph of modern astronomy. Gravitational wave detectors, electromagnetic telescopes, and neutrino observatories are linked in global networks, sharing data and coordinating observations in real time. When a promising signal appears, alerts go out to thousands of astronomers worldwide within seconds. This kind of coordination was impossible just decades ago before high-speed internet and automated data processing. The observation that gravity travels at light speed has philosophical implications beyond physics. It tells us the universe operates according to consistent, comprehensible laws. The same speed limit applies to all forces, all influences, all causal connections. This universality suggests deep underlying principles governing reality, principles we can discover through observation and reason. This consistency gives us confidence that the laws of physics we discover on Earth apply throughout the universe. The gravitational waves we detected traveled for 130 million years across vast cosmic distances, through different gravitational environments and cosmic epochs, yet arrived behaving exactly as Einstein's equations predict. The universe doesn't arbitrarily change its rules in different regions or at different times. Physics is universal. This universality enables cosmology and astrophysics. When we observe distant galaxies, we assume the light they emit follows the same electromagnetic laws as light on Earth. When we model stellar evolution, we assume nuclear physics works the same in stellar cores as in our laboratories. These assumptions could be wrong, but consistent observations over decades support them. The universe appears to be fundamentally lawful and comprehensible. Some philosophers have wondered whether the laws of physics could have been different, whether we live in one of many possible universes with different physical constants and forces. This multiverse speculation is controversial, with no direct evidence supporting or refuting it. But if multiple universes exist with different physics, we happen to inhabit one where gravity travels at light speed, where the fundamental constants have values allowing stars, planets, and life to exist. Whether or not other universes exist, we can study ours. And what we find is remarkable. The universe operates according to mathematical laws we can discover and understand. This unreasonable effectiveness of mathematics, as physicist Eugene Wigner called it, is itself mysterious. Why should nature follow mathematical principles Why should creatures like us, evolved to hunt and gather on African savannas, be able to comprehend cosmic truths through abstract reasoning? These questions touch on deep mysteries about the relationship between mind and matter, mathematics and reality, knowledge and existence. The fact that we can predict gravitational wave signals using equations developed a century ago, then detect those signals with exquisite precision, suggests a profound connection between mathematical structures and physical reality. Mathematics isn't just a human invention for describing nature, it seems to capture something essential about how nature actually works. Let me tell you about how gravitational wave observations are opening entirely new research directions. Before LIGO, astronomers studied black holes and neutron stars primarily through electromagnetic radiation from matter falling onto them. This tells us about accretion physics, how gas heats up and radiates as it spirals inward. But it doesn't directly reveal the black hole or neutron star's fundamental properties. Gravitational waves, by contrast, come from the objects themselves, from their motion through spacetime. The waves encode information about masses, spins, orbital dynamics, and even internal structure for neutron stars. This is completely complementary to electromagnetic observations. Together, they provide a far more complete picture than either could alone. For neutron stars, gravitational waves can probe internal structure in ways electromagnetic observations cannot. As two neutron stars spiral together, tidal forces deform them, raising tides similar to how the Moon raises tides on Earth. The amount of deformation depends on the equation of state, the relationship between pressure and density in neutron star matter. Stiffer equations of state produce less deformation, softer equations produce more. This tidal deformation affects the gravitational wave signal in subtle but measurable ways. By carefully analyzing the waveform in the final moments before merger, physicists can determine how easily the neutron stars deform, constraining the equation of state. This tells us about nuclear physics at densities impossible to achieve in any Earth laboratory, densities higher than atomic nuclei, where our understanding becomes uncertain. The 2017 neutron star merger provided the first gravitational wave constraints on the equation of state. The analysis suggested neutron star matter is moderately stiff. Softer equations of state predicted more deformation than observed, while very stiff equations predicted less. This single observation ruled out entire classes of theoretical models, a remarkable achievement from detecting spacetime ripples lasting less than a minute. Future neutron star merger observations will refine these constraints further. With dozens or hundreds of detections, we'll map out the equation of state across a range of masses and conditions. We'll learn whether all neutron stars have the same internal composition or whether it varies depending on mass. We might discover phase transitions in ultra-dense matter, sudden changes from one state to another as density increases, similar to how water freezes into ice, but far more exotic. These discoveries about nuclear physics at extreme densities have implications beyond astronomy. Understanding how matter behaves at nuclear densities informs nuclear physics on Earth. The same theoretical frameworks describing neutron star cores also describe the quark-gluon plasma created in particle accelerators, the cores of massive atomic nuclei, and the early universe microseconds after the Big Bang. Neutron stars are cosmic laboratories where nature performs experiments we could never replicate artificially. The observation that gravity travels at light speed also informs our thinking about cosmic inflation, the theory that the universe underwent exponential expansion in its first fraction of a second. Inflation would have produced gravitational waves with characteristic properties. If these primordial waves are detected, they would carry information about physics at energy scales trillions of times higher than particle accelerators can reach. During inflation, quantum fluctuations in the gravitational field would have been stretched to cosmic scales, becoming classical gravitational waves. These waves would have propagated at light speed from the moment of their creation, carrying information about the inflaton field, the hypothetical field driving inflation. Detecting them would confirm inflation happened and reveal the energy scale at which it occurred. Various inflation models predict different gravitational wave signatures. Some predict strong signals potentially detectable by future experiments. Others predict signals too weak to ever observe. Some suggest inflation produced particles that became dark matter. Others propose inflation created the matter. Antimatter asymmetry, explaining why the universe contains matter, rather than annihilating into pure radiation. Each model makes predictions that observations can test. The search for primordial gravitational waves continues through multiple approaches. Ground-based detectors like LIGO are not sensitive to the low frequencies where primordial waves would appear, but space-based detectors like LISA might detect them. Experiments studying the cosmic microwave background search for subtle polarization patterns that gravitational waves would imprint. Pulsar timing arrays, networks of precisely monitored millisecond pulsars, look for correlations in timing variations that would indicate gravitational waves at very low frequencies. Each approach probes different frequency ranges and different epochs in cosmic history. Together, they're assembling a comprehensive picture of gravitational wave sources across all frequencies and distances. It's like going from hearing only middle C on a piano to hearing the entire keyboard. Each frequency reveals different phenomena, different physics, and different aspects of cosmic evolution. Let me share something about the technical challenges in detecting gravitational waves. LIGO's mirrors must be isolated from vibrations to extraordinary precision. Earthquakes anywhere on Earth create seismic waves that could swamp gravitational wave signals. Ocean waves crashing on distant shores create vibrations that travel through the ground. Wind, traffic, logging, even human footsteps produce noise that must be filtered out. LIGO's mirrors hang from elaborate suspension systems, multi-stage pendulums that isolate the mirrors from ground vibrations. The systems filter out frequencies above a few hertz, allowing the mirrors to hang almost completely still relative to the ground's constant shaking. Inside the vacuum chambers, the mirrors float as if in deep space, responding primarily to gravitational waves rather than terrestrial disturbances. But even this isn't enough. Quantum mechanics creates fundamental noise limits. Photons in the laser beams have momentum, and when they reflect off mirrors, they impart tiny momentum kicks, radiation pressure noise. Fewer photons would reduce radiation pressure, but increase shot noise from counting statistics. LIGO must balance these competing noise sources operating at the quantum limit, where further improvements require squeezing quantum states of light. Squeezed light is a quantum optics technique where uncertainty in one property is reduced at the expense of increased uncertainty in another. By squeezing the quantum state of light entering the interferometer, LIGO can reduce noise in the precise measurements needed to detect gravitational waves. This sounds like science fiction, but is now standard technology. LIGO uses squeezed light to improve sensitivity, literally using quantum mechanics to observe cosmic events billions of light years away. The fact that we can detect gravitational waves at all, that we've built instruments sensitive enough to measure space-time distortions smaller than atomic nuclei, is a testament to human ingenuity and the power of science. We identified a theoretical prediction, developed the technology to test it, built the instruments, made the observations, and confirmed the prediction. This is how science advances, theory and experiment working together, each informing the other, gradually revealing nature's secrets. The speed of gravity measurement also connects to broader questions about symmetries in nature. Physics is full of symmetries, situations where changing something doesn't affect the outcome. For example, the laws of physics are the same everywhere in space, spatial symmetry, and the same at all times, temporal symmetry. These symmetries aren't arbitrary, they're connected to conservation laws through Noether's theorem. Spatial symmetry leads to conservation of momentum, temporal symmetry leads to conservation of energy, rotational symmetry leads to conservation of angular momentum. These connections between symmetries and conservation laws are fundamental to how physics works. The fact that gravity travels at light speed reflects underlying symmetries in how spacetime is structured. Lorentz invariance, the symmetry underlying special relativity, requires that the laws of physics are the same for all observers moving at constant velocities. This symmetry demands a universal speed limit, and massless particles must travel at exactly this speed. The observation that gravitational waves travel at light speed confirms that gravity respects Lorentz invariance, at least to the precision we've measured. Some quantum gravity theories predict tiny violations of Lorentz invariance at extremely high energies or short distances. If true, gravitational waves at different frequencies might travel at slightly different speeds, with higher frequency waves traveling slightly faster or slower than lower frequency ones. Current observations show no such dispersion, constraining how much Lorentz violation, if any, actually occurs. Each observation tightens the constraints, limiting the space of viable theories. Here's something that beautifully illustrates how interconnected physics is. The same mathematical structures describing gravitational waves also appear in completely different contexts. The wave equation governing gravitational wave propagation is similar to equations describing sound waves, electromagnetic waves, and quantum mechanical wave functions. The mathematics of oscillating systems, resonance, and wave interference applies across all these domains. This mathematical unity suggests deep connections between apparently different phenomena. The principles governing how disturbances propagate through any medium, whether air, electromagnetic fields, or spacetime itself, share common features. Understanding one domain often illuminates others. Techniques developed to analyze electromagnetic waves informed gravitational wave detection methods. Quantum mechanics developed for atomic physics now helps reduce noise in gravitational wave detectors. The observation that gravity travels at light speed fits into this broader pattern of unity in physics. Different forces and phenomena, seemingly unrelated, follow similar mathematical principles and share common features. This hints that underlying reality might be simpler than it appears, that the diverse phenomena we observe emerge from a smaller number of fundamental principles and entities. String theory takes this unity to an extreme, proposing that all particles and forces arise from vibrations of fundamental strings. Different vibration modes produce different particles, an electron here, a photon there, a graviton somewhere else. If true, the fact that gravitons travel at light speed would reflect their masslessness, which would emerge from the string's vibration mode, which would be determined by the theory's underlying mathematical structure. We don't know if string theory is correct. It remains unverified by experiment, with critics questioning whether it's even testable, but the search for unity in physics drives much theoretical work. Physicists believe, based on centuries of successful unification, that nature at its deepest level is elegant and simple. Complexity emerges from simple underlying rules, just as the richness of chemistry emerges from quantum mechanics and electromagnetism, or the diversity of life emerges from the simple rules of evolution and genetics. Let me tell you about the human side of gravitational wave discovery in a way that captures its emotional impact. When the LIGO team announced the first detection in February 2016, many of the scientists involved became emotional. Some had worked their entire careers, 30, 40 years toward this goal. They had faced skepticism, funding challenges, technical setbacks, and the very real possibility that detection might not happen in their lifetimes. Seeing the signal, confirming it was real, and announcing the discovery to the world represented the culmination of decades of effort. For some, it was the defining moment of their professional lives. The standing ovation that erupted at the press conference wasn't just celebrating a scientific achievement, it was recognizing the human dedication, perseverance, and collaboration that made it possible. I find this deeply moving. Science is often portrayed as cold, objective, impersonal, just facts and equations. But real science is done by real people with passion, curiosity, and dedication. The confirmation that gravity travels at light speed isn't just an abstract fact. It's a victory of human curiosity over cosmic mystery, of ingenuity over technical challenges, of hope over skepticism. It's people working together across decades and continents to answer a question that Einstein pondered a century ago. This human element reminds us that we're all part of the scientific endeavor. Professional scientists do the detailed work, but they're answering questions that belong to everyone. Where did we come from? How does the universe work? What are we made of? These aren't just academic questions, they're deeply human ones, arising from our capacity for wonder and our drive to understand. When you learn that gravity travels at light speed, you're not just acquiring a fact. You're connecting with centuries of human inquiry, with Einstein's genius, with the engineers who built LIGO, with the neutron stars that merged 130 million years ago, and with the fabric of spacetime itself. You're part of a species that can detect ripples in reality smaller than atoms and use them to understand cosmic truths. And that's something worth celebrating. If you made this far, make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I am sure you will love this other one at the left side of the screen. This is why we can't travel at light speed. Discover how time dilation, mass increase, and the fabric of space-time itself conspire to keep us forever below the speed of light. See you there.